Have you ever watched one of these robot dogs and just been completely mesmerized? They move with this incredible, almost lifelike grace that's kind of hard to look away from. So let's do something fun. Let's pull back the curtain and really reverse engineer how they do it.
I mean, just look at this motion. It's not just a clunky machine stomping around, it's this coordinated dance of metal and circuits. What you're seeing here is a trotting gait, where the diagonally opposite legs move in perfect sync. It's bio-inspired robotics at its finest, literally taking notes from the animal kingdom to solve really complex engineering puzzles.
So that's the big question, isn't it? It's one thing to see it in action, but it's a whole other thing to understand the blueprint underneath. How do you program a machine to have rhythm? How does it even balance? Well, that's the mystery we're going to solve today. We're going to break it all down piece by piece.
Okay, first things first. Before a robot can walk, it needs a body, right? We have to start with the physical hardware, the skeleton that makes all this amazing movement possible in the first place.
I love this slide because it shows the whole journey, from an idea to a real thing. On the left, you've got this perfect, clean 3D model from a computer. And on the right, the finished prototype. You can see it's built from a mix of materials. There's acrylic for the strong central body, some lightweight plywood for the legs, and even aluminum for the motor mounts to make sure everything is precise. Nothing is random. Every material is chosen for a reason.
Now, to really understand how it moves, we need to talk about a core concept called degrees of freedom, or DOF for short. The easiest way to think about it is to just look at your own arm. Your shoulder can move up, down, forward, and back, and your elbow can bend. Each one of those independent movements is a degree of freedom. So for this little robot we're looking at, the magic number is 8. It's got 4 legs, and each of those legs has 2 degrees of freedom, 2 joints. One joint acts like a hip, swinging the leg forward and backward. The other one works like a knee, lifting the leg up and down. That really simple 2DOF design is the entire foundation for all its complex movements.
Okay, so we've got the skeleton, we've got the joints, but a pile of parts doesn't just get up and walk. So how do you turn all that hardware into fluid motion? The secret, as it turns out, is all in the math.
This is the fundamental problem that engineers run into. If you just tell a motor, hey, move to position A, then B, then C, what you get is that classic, jerky, clunky robot look. So the real challenge is, how do you create a smooth, continuous, and repeating pattern, a gait that actually looks natural? And the answer is this absolutely brilliant mathematical tool called a Fourier series. The best way to think of it is like a recipe for motion. You take simple ingredients, in this case basic sine and cosine waves, and you just mix them together in exactly the right amounts to create any complex, repeating pattern you want. It completely transforms a choppy list of commands into a smooth, perfectly blended recipe for movement. And this graph, this is the result of that Fourier recipe. You are literally looking at the sheet music for the robot's dance. Each of those smooth, rolling waves is a command being sent to a leg motor, telling it precisely where it needs to be at every single moment. That's how you get a nice rhythmic gait instead of a clumsy shuffle. All right, the robot is moving smoothly. Awesome. But there's another huge problem we haven't talked about yet, gravity. How does it stay upright without just, face planting? This brings us to the crucial topic of stability. It turns out there are 2 main ways a robot can stay balanced. The first is called static stability. Think of a turtle. It's slow, it's steady, and it's always stable even if it stops mid-step. The other approach is dynamic stability. And that's us when we run. We're basically in a constant state of controlled falling, using our forward momentum to stay balanced. It's way faster and more efficient, but it requires much more complex active control. This diagram here explains static stability perfectly. Just imagine the robot has 3 feet on the ground, and those 3 feet form a triangle. As long as that little black dot, its center of mass, stays inside that triangle of support, it simply will not tip over. For a project like this, going with static stability is a really smart choice. It simplifies the programming a ton and lets the builders focus on perfecting the walking gait itself, instead of also having to tackle the much harder problem of dynamic balance. So we've covered the body, the math, and the balance. But here's what might be the most exciting part of all of this. This isn't just technology for advanced research labs anymore. Thanks to an incredible community of makers, you can actually build one of these yourself. This quote from an Instructables guide just says it all, doesn't it? What once really seemed like science fiction is now an accessible, hands-on STEM project that you can do.
The barrier to entry for robotics has completely crumbled, and that is just incredibly cool.
And the process isn't as scary as it sounds. It's been streamlined into 4 basic steps. First, you download everything you need, the design files, the code, all of it. Then, you assemble the physical parts, almost like a high-tech Lego kit. Step 3 is crucial, calibration. You have to tell all the motors where home base is, so they can all move in harmony. And finally, the magic moment. You upload that motion program we talked about, and you watch your creation take its very first steps.
And the reason this is all possible is that you don't have to reinvent the wheel. Groups like the Open Dynamic Robot Initiative and just countless creators on platforms like GitHub are sharing everything: the design files, the software, the build guides. It's this amazing global collaborative effort that's pushing the entire field of robotics forward at a mind-blowing pace. So let's just do a quick recap. First, the blueprint. A simple body with 2 degrees of freedom legs is all you need to start. Second, the rhythm. That comes from the math, using a Fourier series to create smooth, natural gaits. Third, the secret to balance. It's all about managing the robot's center of mass. And finally, and maybe most importantly, the access. This incredible tech is now open source and available to everyone.
So we've seen the blueprint, we've seen the math, and the mechanics. But understanding how these things walk just opens up an even bigger question. As this technology gets more advanced and more accessible to everyone, what problems are they going to solve next? Where are we going to see them exploring? The possibilities, well, they're just beginning to unfold.